One of my favorite topics in physics is waves and sound. It's the basis for musical instruments, it's the basis for sounds that we hear. Music is all based on the physics we'll talk about in this chapter, chapter 16, as well as in chapter 17. And in this chapter, we will cover, looks like 13 concepts. So in sections 1, 2, 3, and 5 of the textbook, we'll cover 8 concepts. And then in the remaining sections that we're covering, we'll cover the remaining of the 13 concepts. But some very fascinating subjects. The section 16.1, the first section of the book, we're going to talk about the nature of waves. First, we'll define a traveling wave as a disturbance that carries energy from place to place, with particles oscillating about fixed positions. What do we mean by that? We mean that if you take this end of a slinky, a long slinky, and you jiggle it up and down, you can create a pulse that moves forward from left to right. And then if your hand goes up, then down, then up again, you can send a wave along that slinky. That's what we're talking about. So it's a disturbance in that slinky, and it is carrying energy in this direction. So that's the direction of travel. And the particles, these little bits of slinky, you mark off, put a red mark on a little bit of slinky, say for example right here, and you're interested in its particular motion. It does not move in the direction of travel. In this particular case, it moves up and down. But the most important part for this definition is that these particles oscillate about fixed positions. So this little bit of slinky is going to move up, move down, and then move back to where it came, or where it started again. It's not moving with the wave. So a transverse wave is the second concept. Transverse wave is one in which the disturbance occurs perpendicular to the direction of travel, exactly what we were talking about in the previous slide. Direction of travel, direction of the disturbance, perpendicular to the direction of travel. Nothing more to it than that. Longitudinal wave is one in which the disturbance occurs parallel to the direction of travel. So again, here's the direction of travel, but we're taking, instead of jiggling the end of the slinky up and down, we're pushing it back and forth in the direction of, along the axis of the slinky. So where hand comes forward, creates a compressed region that propagates to the right, and then the disturbance in the slinky is in the same direction as the direction of travel. That's how that works. This is a simulation of the difference between longitudinal and transverse waves.
In the longitudinal wave.
So in the longitudinal wave, you can see that that disturbance occurs in the direction of travel of the wave. Whereas for a transverse wave, as will be shown here, the disturbance is perpendicular to the direction of that wave. That's all there is to it. Water waves are a combination of transverse and longitudinal waves. And how that works is that a little bit of water here actually makes a circle as the wave propagates to the right. So it moves up along here, it's moving back at the top, down, and to the side. So it's, since the direction of travel is this way, to the right, it has both a transverse piece, which is up and down, as well as a longitudinal component to the right. So what kind of a wave is this one? We call this the wave. So this is where fans stand up, raise their hands, and then sit back down in the football stadium. This is a world record on the so-called wave. You can see the direction of propagation of the wave is this way. It's the direction the wave is moving. What's the direction of the actual individual disturbance of the people moving? Well, they're moving up and down. The wave is propagating sideways, and so that's going to be a transverse wave. Kind of cute. There's a world record right there. And that's section 1 of chapter 16.